Okay, hello everyone. Welcome to this last plenary session of this conference, which we will start with the ESO report, which Michele Cirasuolo will be giving. The floor is yours, sir.
Thank you. Welcome everyone, and for this last plenary session, I will give you a quite concentrated view of the ESO report, so bear with me. I have to go quite fast to cover all the activities at ESO. And just for the young generation, so ESO is an intergovernmental organization currently with 16 member states all across Europe, plus and Australia as a strategic partners. The headquarters of ESO is in Garching, close to Munich in Germany, but all the observations are done in Chile across the north part of the Andes. And here there are several observatories. You can see here a picture of La Silla and Paranal, where we have 8 telescopes plus 4 smaller telescope for interferometry. Also the sub-millimeter single dish apex up to the plateau of Chaknantor, where is also the ALMA, millimeter sub-millimeter array. And there is a quite comprehensive operations and public archive data that you heard this morning from some of the talks, which is very useful. So please keep using it, which is a very gold mine for research. And then we have the new big program at ESO for the construction of the extremely large telescope, which is the largest optical near-infrared telescope in the world. And finally, the new program for hosting the Cherenkov telescope array in the south. Let me start with a couple of really brief science highlights, not many, just to give you some ideas. So one is certainly the very famous image of the supermassive black hole, Sagittarius A star, observed with the EHT collaboration, of which ALMA and APEX has been a critical and essential component to make this beautiful image, which made a very good impression in the public with a press release at ESO hosted in May. And that also confirmed what was already a breakthrough Nobel Prize Science obtained by Gravity team using the VLTI. And you can see here, overlaid to the image of the black hole, you can see this dot, which are the photo position of when you have a flare that is orbiting around the central part of the black hole. Another very interesting science obtained by the VLT, this time with Espresso, which has confirmed that there is a third planet around Proxima Centauri, with a mass which is a quarter of the mass of the sun of Earth, and that has been is the lightest planet ever found and measured with the technique of radial velocity. You can see here the reference to the paper as well as to the public release that ESO has issued. Just a few updates on the various programs, very briefly. So news on ALMA. As you know, there is a new ALMA roadmap for 2030, which will focus on various science from origin of galaxies to the chemical complexity and the origin of planets. And this is driving what is the update of ALMA itself in terms of bandwidth, and also increasing the sensitivity and the throughput of the system. And that is the major new development of ALMA, which are ongoing and on track to be delivered. News from Paranal instrumentation program. Here there's been quite recently the commissioning of CRIRES Plus, which improved significantly the spectral coverage, 10 times more simultaneous bandwidth compared to old CRIRES, as well as higher throughput. As you can see here, an image of how much more science you can do in a single shot. Also quite recently, and there's been an ESO announcement about this, NIRPS, which is the high resolution spectrograph for the 3.6 meter on La Silla, for high-resolution spectroscopy, and they just achieved first light, and is a very exciting new instrument to be used in combination with HARPS to get you optical and near-infrared coverage for high-resolution spectroscopy. ERIS, which is the new imager and integral field spectrograph at the diffraction limit of the VLT, is also undergoing commissioning, and they're also progressing quite well and achieving good Strel ratio from the images that they have. If you look a little bit in the future, the progress of the 2 new massive multi-object spectrograph, MOONS and FORMOST, are ongoing, and they are planning to have their PAE by the end of next year. You can see here some image of the progress on the MOONS and on the FORMOST spectrograph. Massive spectroscopic capabilities for the communities where you're going to have millions of spectra at your disposal over the next few years. And then if you move even more a little bit in the future, we have the next generation of instruments where we have various instruments being signed the agreements. The first one is MAVIS, which is the multi-conjugate adaptive optics in the visible for the VLT, which will reach the diffraction limit in the optical, in the VR and I band, to achieve even better performance compared to what HST does. And it comes with both imaging and an IFU in the optical. Two more projects, Gravity Plus, which is an upgrade of Gravity to push even further the science of gravity, both in terms of reaching fainter targets, but also increasing the sky coverage. Also, the agreement has been signed and the work is progressing. And also CUBES, which is a high-resolution spectrograph in the UV, is also progressing. The last instrument which has been identified by the VLT 2030 roadmap is Blue Muse, which is an IFU complementing the current Muse by extending into the UV and the blue part of the spectrum. Will start the phase A most likely in 2023, but still to be decided. Let's move on to the big new project, which is the Extremely Large Telescope. The ELT, as you know, will be the largest optical near-infrared telescope in the world. And we have just created a new website, ELT.org, where you can find all the possible information about the telescope itself, the instruments, and the possible science with it. So please visit it and use it as a mine to find information about it. The telescope needs, for the primary mirror of 39 meters in diameter, 798 individual segments to create this primary mirror, and the production is now in full swing. We have more than half of the blanks of the M1 already produced by Schott. You can see here is becoming a factory where you have all these components to be piled up and ready to be polished and integrated. And here you have a picture of the very first segment, completely assembled and polished to nanometer accuracy on the surface, that has been validated and accepted to be then shipped to Paranal. Also, the secondary and tertiary mirror of the ELT are giants. So imagine the Vista primary mirror for the ELT becoming a secondary mirror. Both M2 and M3 are 4 meters in diameter. They're both being produced as a blank. M2 is also in a good state of polishing. You can see here, as well as the cell that will host M2 upside down 60 meters above the primary is in good production in a Spanish company called Cener. The core of the adaptive optics is the M4 and M5, which are really the fast mirror able to correct for atmosphere and for all the disturbances that you have. M4 is going to have more than 5,000 actuators to be able to compensate all the turbulences, and the reference body you can see here has been accepted. Also, all the thin shell and all the modes are ready to be finally assembled. And also M5 that you see here on the right is also ongoing to be produced in various pieces to then to be brazed. Concerning the dome and the main structure, which is one of the largest contracts that we have, is also undergoing, just to put into perspective. So this is the picture of the ELT, and on one of the platform, which is as big as a tennis court, you can actually place one of the UTs. One of the VLTs can fit on one of the platform itself. So it's a massive project which will be hosted in one of the peaks just close to Paranal, which is called Armazones, just 25 kilometers away. And that is the current status of the site itself. You can see here that all the foundation has been laid, and we are actually now building above ground. So these walls that you see on the side are already 12 meters high, and that is part of the construction for the LT. And as well as all the components for the massive dome structure are also in full production. You can see all the steels, the rails that will host the mechanism to move the dome, as well as the anti-seismic vibrations that we have. And both Paranal and Armazones and the ELT will be completely green. So the photovoltaic plant has been completed and will be inaugurated in a couple of weeks. And they will provide green electricity and green energy to both Observatory Paranal and Armazones, which is fantastic. A few words on the instruments. We have already, as part of the construction of the telescope itself, some instruments which are completely embedded in the construction, and these are what we call first-generation instruments, which are the primary imager for the ELT, which is called Mikado, covering the optical, red and optical to near infrared up to K-band. with a field of view of 1 arc a minute, and is fed by a module, which is an MCAO module called Maori, which actually is changing name into Morpheo. And it's getting towards the final stages of their final design review. Mikado and Maori is entering the final design review. For people interested in spectroscopy, the primary instrument is Harmony, which is the integral field spectrograph for DLT, again covering the red and optical and the near infrared with a variety of scales and resolving power. And finally, for science regarding the mid-infrared, there is METIS, which covers L, M, and N band, both in imaging as well as in spectroscopy. That is what we call, these instruments which are into the construction, but because we also want to provide to the community a better coverage of the parameter space, we also started the phase A, and we are towards the beginning of the phase B, also for 2 new instruments. One is a high-resolution spectrograph called ANDES, which will cover a resolution of 100,000 optical and near-infrared. And then a multi-object spectrograph, again, optical and near-infrared, called Mosaic, with medium and low and medium resolution, again, covering similar wavelength range. If you want to, from an astronomer point of view, have a look at the capabilities of the ELT, you can have here a plot of wavelength coverage as a function of imaging and resolving power. And as you can see, with all these instruments, first and second generation, we really cover quite nicely the parameter space that is offered to the community, both in imaging and in spectroscopy at the various resolving power. And for me, what is the most important thing is that the ELT will really open up a new parameter space in terms of observation at the diffraction limit. So a diffraction limit at the ELT is just 5 to 6 milli-arc second in J-band, at 1 mass, and 10 milli-arc second in H. So we're really opening up a massive parameter space. These are just few examples of the type of science that the ELT will be doing at the diffraction limit. We'll be able to observe, planets in our solar system even better than ESA missions, and we are really looking at synergies on how we can combine missions with observation from the ground with high resolution. But also, for example, in crowded field, where you have observations of crowded field which are limited by your beam, by your PSF, again, the ELT will be unbeatable. And also to looking at the buildup of galaxies, for example, where ELT will be able to resolve the individual building block of galaxies at high redshift. And just to give you an example, we have been looking in this symposia that, in the local universe, we can do parsec, tens of parsec science. With ELT, we'll be able to do the same science, but at redshift 2, with resolution of the order of 50 to 100 parsec rest frame. Just to give a perspective to the young generation, but also to see how ESO connects with the scientific community, we have a quite vibrant students and fellowship programs. So really, we encourage you to come, almost done, really encourage you to come and join us with this program, both spending one or 2 years at ESO as a student or applying for the fellowship applications. And you have, if you are interested, so please pass by the ESO booths. There are plenty of postcards that you can take with you and distribute into your institute and to the young generation. And finally, if you have any high impact or curious results from your science, again, contact us. The communication department is very eager to hear you, to see if this can be made into a public release. So please contact us. We are very keen to help in distributing your results. And I stop here, really hoping that this birthday of 60 years for ESO is a big celebration of your science, and we hope that together we keep the next 50 or 60 years to equally good science and equally good, really state-of-the-art instrumentation and science from the community. Thank you.
Thank you very much. And because we're on a very tight schedule, any questions you have, Michele will be at the ESO stand after the session, but even at the moment, probably there is somebody there who can answer your questions. So thank you again. So we're very fortunate. In this meeting, we didn't have just one talk from a Nobel Prize winner. We have two. And this one is going to be by Didier, and he's going to talk to us about exoplanets and life in the universe.
Thank you. Thank you very much. So it's a pleasure for me to be here. I think I'm so thrilled to meet all this young generation showing up in this kind of meeting. So if you want to talk to me, please, do not hesitate to reach me. So what I will try to do in this talk is to explain what has happened really here. I think we are in a kind of a situation where I think we are moving into a new realm, which is from detecting other planets and other stars into questioning the emergence of life and why we have life on Earth. Is the universe full of life? There is a big stretch between the two, but what I would try to convey to you right now is to explain the pathway, because there is ongoing work and serious work that has changed completely the perspective on this, and I do believe we are on track to answer these kind of big questions, and the astronomers are playing a very, very important role into that, but they will not be alone to be doing this. So let's start with the basics, and you may have seen this diagram early on. This is a bit the snapshot, what we have learned about exoplanet. We're using very few parameters: the mass of the planet, the size of the planet, and the period of the planet. All the points you hear, all the dots, are data. There is no trick, there is no model. These are the real measurements. We measure the size of the planet, the mass of the planet, and the period of the planet. The color depends on the technique being used, but that's really what we've been doing. So it's fair to say that we have been lucky, or nature has been kind and nice with us. Because essentially, in a way we can approach and detect the planet, we're limited. Essentially, we're limited to the left side of this diagram, just by the various elements of the techniques, the statistics of the transits, and various aspects in the way we approach a problem. We understand quite well the limits, so it's kind of a threshold, and it depends a bit of the equipment. But to make it short, it's pretty obvious. You compare to our own planets, we have not reached our planets. We have not reached the solar systems. We're reaching planet that looks like some of the planet in our solar system, but we're far, far away of detecting a solar system equivalent. And in that sense, it's quite amazing, because 30 years ago, everybody was expecting the planet to be like the solar system. And nature has been kind, because they have shown off that it's not the case. Actually, when you run to the math, and there's a lot of debates where you do the statistics, I don't want to just go too much into the detail, but there is a vast majority of the stars. This is a fraction of planet you have on stars. And the stars I'm talking about are not very different from the star like the sun here, roughly speaking. So clearly there is a vast majority of stars that have planets which are different. Well, we have this very rare and extreme case of the hot Jupiter on the top. We have these amazing populations of what we qualify, depending on your attitude and the way you look at this, is super Earth, mini Neptunes, and mini Saturns. It's a bit up to you, but that's really something that lies into a diagram here. There is no counterpart in the solar system. That is a piece of luck, because without this, I will not be talking in front of you today, and exoplanet science will be still looming somewhere, but certainly not at the heights it is going right now. So we are in a very exciting days, because we are in a system that have produced life, but so far, most of the system we have found are different. And this is a very exciting moment, because we have to redefine a little bit how we use that, how we compare this. And that's a bit the purpose of the talk. What do we do now? What do we do when we have this situation? Of course, people are working hard, and they will, in the next 10 to 20 years, expand this. They will increase the detections, and there's clearly a lot of great program and project that will improve, and eventually we will find, hopefully, planet like our solar system, because I can't believe we are just the only Earth-like in such a period, and in the universe. But it's still a very fascinating question we are right now. So what can we do about life? How can we use this diagram? Well, another element which is fascinating is I think we have changed the perspective. We move from the dots or points into real astrophysics. In a way, we're talking about density. So again, this is real data with the error bars. It's a collection of the mass and the size of the planet you get when you compare and you combine the transits and the Doppler radial velocity techniques to get the mass of this planet. Well, you compare with this various model. On the top is the one of Jupiter, so it produces well Jupiter. The one green at the bottom is the Earth. And then the one in the middle, between the blue here, it's kind of a hypothetical planet, which is kind of made of water, doesn't really reflect clearly. But what is pretty obvious here, we're facing a very interesting cases where there are planets, clearly, that looks like the planet of the solar system, but not quite like. They are kind of different. And if you sit up just above Neptune, you realize, should I use the laser here? Right. So, does it work? Okay, right, thank you. How does it work? Here we are. Right, so if you sit here, you clearly understand that Neptune is already very different here from the model you have into Jupiter and Saturn, and it's pretty clear there is a whole range from Neptune down to reach the Earth. And what is fascinating is very populated with systems here that have mass and size within the regime that you would qualify as Earth-like or Earth-ish-like. And that is very interesting because it's really defining the complexity of the diversity of the planetary system. Of course, the caveat we have to keep in mind, most of the systems, they are the ones that I've shown before. So they are short period systems. Most of them, they're very highly irradiated by the star. It means if you compute the equilibrium temperature, just on the principle that you absorb all the energy from the flux, from the stars, you reach quite substantial hot temperature, much hotter than the one we have in the solar system. But there are some cases when it's kind of mild because the star is not exactly like the sun. And when you move down to low mass stars, you have system which is in short period. One of them very famously known is TRAPPIST one. I'm sure you have seen it during this meeting. And this system is kind of a point of focus here. So this is where we are. We're doing astrophysics. We're doing astrophysics of the physics of the planet. What can we do next? What is going on next? So very fortunate because we have fantastic equipment that we can use, and we can use this very special geometry when the planet is transiting. So when you have the transit, you have these two very specific moments. They are short. It's not super efficient because you are limited by the time of the transit. But there's a moment when the planet goes in front of the stars, and then you get what's called a transmission spectroscopy. There are some part of the intensity on the flux from the star that cross the atmosphere and produce the same effect you have when the sun sets on the sunrise. It can change the color of it. It gives you a different size of the planet. By the way, transmission spectroscopy doesn't measure spectra. They measure size. And you have to convert the size into a spectroscopic information, which is kind of a skill and something that people are doing, and they are doing these days. There's this moment when the planet is behind. It's quite interesting to think about that. I mean, when you look at the system with the planet, you end up with a system where essentially you have always the planet around. If you want to make sure that when you measure the system, there's only the star, and you really want to have a reference as a star, you have to wait the planet is behind, and that's the trick. If you wait the time when the planet is behind, and you just look when the planet goes out, then you end up having the direct measurements of the emerging flux for the planet. Whether it's reflected flux or whether it's a thermal emission, it depends exactly on the condition and the composition of the atmosphere. It depends on the wavelength you observe. Essentially what you get. If you're lucky enough, you can track the planet along the orbit. And you get something similar to the moon, you get the phase functions, and then you have the chance to detect the dark side and the night side of the planet. So it's quite fascinating, and what is even more fascinating is this is something that can be targeted. And there are major equipments that we've heard about a lot during this meeting, so I think that will play a key role here in the next 10 years about this. Obviously, the big telescope, the ground-based telescopes, the James Webb Space Telescopes, and the next generation, here's Ariel, that I'm picturing, that will be using these techniques to extract spectroscopy. So what does it mean when you extract spectroscopy of a planet, of the atmosphere of a planet? Well, it depends a bit of the planet you're talking about. This is a series of planets going from Neptune down to the Earth, and I just gave you some example how it may look like. This is a diagram that I stole from my friend Madhu Sudan, just to demonstrate that depending on what you have to deal with, I think here you see it with the color of the planet, you can have a drastically different kind of emerging spectra, or you can have a different spectra that you measure through absorptions and transmission spectra to the planet. So it's all about what is a planet. Of course, you have to combine that with the density of the planet because you only see a bit of the outside of the planet. It's all about playing with that, but it's pretty clear that having the information about the physics of the planet and the spectroscopy of the planet, you will be in a situation when you can start thinking about the planet as a global entity and trying to ask yourself, what do we know about these planets? And I just, a bit for understanding what I mean, I just use the Earth at the end. At the end, the one on the extreme right, this one is the Earth. It's the Earth when you look at the reflection of the Earth, and that's the one when you want to consider wavelengths, which are not dissimilar from the wavelength you can get from the ground. I could have picked other wavelengths, but I picked this one on purpose because that's the one you will do very well from the ground-based astronomy. And it's quite interesting to see there's a lot of feature here. It's not the purpose of the talk, and it's not my expertise to talk about that, but what I would like to convey here is I think with the amount of element we have, with the amount of tools we have access, we can do that. Of course, it depends of the brightness of the stars, it depends on the type of planet you will do, but they will be, and there is already a significant number of spectroscopy being done on atmosphere of planet. Essentially, they are big planet right now, but they're moving down to Neptune, and it's pretty clear with the new equipment, they will be moving down to smaller planet. There is really a tendency, and there's an increase of data. Okay, so we have planet, we have small planet, we have spectroscopy. What do we do with that? When can we start talking about what's going on the planet? What about detecting life? So if you are in the planet business, there is kind of a joke always. I mean, there has been, if you look back in the past, at least 30 times, first discovery of a planet, you can host life. It's quite funny. There will keep being more. I'm pretty sure you will keep doing it because it's fun and the media loves it. And that's actually, it's a question that you can ask yourself. What does it really mean, detecting life? What can you say about life? And I personally must say that I was telling story that was completely wrong and completely rubbish in the last 20 years about that. And the reason why I've changed a little bit the approach, because I've been talking with people that know much better what is life, which are not astrophysicists, actually, are people that are dealing with life. It's biologists, chemists. I mean, people working with Earth, working on the Earth and working on the planet, other planets of the solar system. And that's the story I would like to tell you right now. How do we do, as an astronomers, how do we connect what we're doing, what we will be doing, with the question of life? And I think there is a pathway. It's a very exciting pathway, and I would like to share that. The first message I would like to convey to you, I took two great figures about, one about the physics and the other one about the origin of life. The first one is this statement for Etienne Moser. Etienne Moser was of the pioneer trying to find out, how you can assemble life from chemistry. And he came up with something very clear. Well, there is no way you can discover life, at least the way we know life on Earth, because there is no traces, there is nothing left. And if you believe you will use Extremophi to tell you about life, it will tell you that whole life has explored all the possible niche, ecological niche, but it will tell you nothing about what is the intrinsic beginning of the life. The only way to make sure you are doing it is to just reinvent it, to make it in the lab. And I follow this statement from Richard Feynman that says, well, if I cannot create it, I do not understand. And I think there is right now a complete transformation in the game right now. There are people in the labs that are making life, at least they're trying to make life, to reproduce the life that we know it. And that is a completely changed situation. But they're doing that in a concept when they're trying to reflect with the new developments of the astrophysics in this field. And that has a profound consequences on our work and the way we're going to observe the planet and the kind of work we are going to do in the next decade. Well, let me give you a very simple one-on-one on what I mean beginning of life, making life. Well, we know only kind of life, the life we have on Earth. That's the only one we know, so this is the statement we have to accept. Let's focus at least on that one. If you can make that one and reproduce that one the way it started, it's a good start. It doesn't tell you the whole story, but at least you start from somewhere. Now, the idea of making life is something that chemists are doing in a lab. But life is not done in a lab, it's done in the dirt. It's doing everywhere on the planet. And you have to make it work in a dirty environment. And dirty means it's a wild environment, it's an aggressive environment, so you have to win. The chemistry of life should be the dominant one. If you don't win, the chemistry will be anyway happening, but you will end up with something different. You will end up with a shampoo or whatever, but you're not going to end up with the molecules that will drive to life. So there's a couple of assumptions that people have started to assemble and to do the chemistry. And what is really fascinating, and they come up with something which is very close to what we are doing in terms of astrophysics. They come up with the fact that you need water, and it's pretty cool because water is something we can detect. They need also something that you can connect to the volcanic activities, and in that case, SO3, there's a couple of others, but that's one that is being used in the productions. HCN. HCN doesn't look like something that is connected to life. I mean, if I drop a bit of HCN in this audience, that would be in the news because everybody would be dead. So you don't really want to do that, right? But actually life needs that, loves that, because it's a very energetic process. It turns out that there's a lot of HCN in comet. And it turns out that the origin of the solar system is a lot of comet falling on Earth. So all this delivery element is something related to astronomy, is connected to life. And you need some kind of neutral atmosphere. And that's a major change compared to what has been going on in the last 40 years, where the assumption was there will be much more energy into the atmosphere. So you assume that the atmosphere in that case doesn't give you any energy. So chemistry needs energy, right? If you want to do chemistry, if you want to do cooking, you need to do something. And you need to shake, you need to boil, and you need to do something. So the energy here, where do you find it? Well, it's pretty simple. You use the sun. because the sun early on produced a significant amount of UV, which is bathing the planet. So you have all these ingredients on the surface of a planet. And actually what is magic is just word, and people have set up reactions, and they have demonstrated it works. At least it works to some extent to produce the basic ingredient of life. So if you want more detail, you can refer to this paper and that one. This is what it looks like in chemistry. So don't even try to look where is the start here. It's a red HCN here, right? The reason why I show you that is because it demonstrates that with a network of reaction, you produce the amino acids, it's the green stuff, you produce the lipids, which is the yellow stuff, and you produce your nucleotides, which is what is being used by the genetic codes, which is the blue stuff. So everything is built up at the same time by a network of reaction. It's possible because these days people are using computers to do chemistry, so they produce chemistry of network into computers. It's a new kind of chemistry. They have equipment you cannot even dream 20 years ago. They can analyze, hundreds of residual at the same time, and we know that with the COVID and how quick it is to analyze now, to sequence a genetic sequence. So they are doing that really there. And they have much more tools. So they were able to put up together a network of reaction producing the basic ingredients. This is not life. This is just the bricks of life. So at some point, you will have to demonstrate that this is assembling. And there are work I cannot talk about. I can tell you there are stuff assembling here. There is element. I will not be surprised if in the next 10 years, somebody is going to claim they have been able to demonstrate life, at least to make a live chemistry corresponding to the chemistry of life we have and we know on Earth. So it's quite fascinating, this, because it connects something that you would have never thought it would be possible. It's the chemistry of life, the way we know it, and the planet. And actually, they bound together, because life is connected to the planet. We know that too much. I think it's difficult to leave this planet. You have to fight the gravity. You will not survive. As soon as you get out, you just die. So there is no way life just isn't disconnected from the planet. We're intimately connected to this planet, so we have to solve the problem together. And you can imagine that maybe there is different kind of life for different planet. You can imagine there is a kind of optimum versions of the chemistry. I don't really know the questions, but I think what is interesting here is you can start connecting all this together. So how do you do that practically? Well, you have to open your mind and you have to look about other planets as well. That one. That's quite an exciting day. And when you think about that, last time we have been on the planet bringing back sample was in the 60s, on the early 70s. It's more than 50 years ago. We brought back piece of the moon, demonstrating the moon is the same bits of the Earth, and actually was the productions of the early Earth, and a major impact that just extract the Earth structure and made the moon. So we're going to do that on Mars. Of course, we're studying the structure with the robots, but the kind of equipment that you are using there is nothing to be compared with bringing back the stuff here and the equipment that is available on Earth. What is fascinating, and you don't need to be to understand very much about the geophysics or the geology of Mars to understand we're talking about a basin, of a fluvial basin here. It was a water flow here. You have, and that's the reason why the robot is there. It's the reason why J0 crater has been selected. It's the reason why the theory I was mentioning was used as a key element to drive the selection of the site. The idea here is because Mars was like that after 1 billion years, essentially, there must have been life somewhere also started, or at least some chemistry of life on Mars. Because Mars it's not exactly a copy, but it's not so far away from the Earth. So the robot is going to bring back sample, and we're going to analyze this sample and to look for isotopic differences, some element of the chemistry of life that we believe can be connected to life. We know already from the rocks they have a study with the robots that it was full of water. So the water question is solved right now. There has been a couple of papers on that, so there's still water on Mars, there's some left, but there has been really this stage. And Mars is a very fascinating point when you can bring stuff. So it demonstrates already that we can extend the knowledge by comparing. What we're going to see, I don't really know, but it would be interesting to realize whether there is a similar chemistry. If there is indeed a similar chemistry on a planet which is not exactly the same, that would be an interesting input already, telling us that maybe we can expect this kind of chemistry a bit everywhere, and if the planet is kind of a similar build-up. And there are some differences, which is just part of the interest here. So Mars is one part of the story. The other one is trying to connect all the dots together. So the way to connect the dots needs to go back to the Earth. So if you're not familiar with the history of the Earth, you have to talk with a scientist, and they will show you that kind of diagram, which is kind of the Earth seen in 4 different times. When you start early on, which is what we're doing, this is our core business. This is that part which is nebular phase, which is what we're studying, formation of planets. bombardments, and you have this early stage we can also study, because at that time there's a lot of change into the atmosphere. The atmosphere is evolving very quick. We lose the hydrogen and helium. I think the heavy element are sinking down and create the core. There is a lot of impact at that time that constantly change the atmosphere, are bringing a lot of carbon, which is interesting because this is something that we want to build a life on. This is why we have so many carbon on Earth, and it's because there's a lot coming and falling as well on Earth. And then it's cooled down, and then at some point you start the plate tectonic mechanism here, and you are into this very interesting situation with the mixing of this neutral atmosphere, CO2, SO3, and water, and then at some point you start something which is related to the prebiotic chemistry leading to life, or not. You can end up also with mineral life. What is fascinating here is there is only one Earth, and everything down in the past is gone. We have no traces at all of what has happened. We don't even know what exactly if this is the case. But we can study a lot of other planets at different time, at different age, in different conditions, with different mass, with different size. So I think the fact we have access to these formation processes, we have this wonderful image that I'm showing here, and we have so many planets, helps you to expand the view. Of course, you will never reach the detail of the Earth, but you have the numbers here. Mars is an interesting landmark, and then you can connect that with the chemistry. And what we could do in terms of astronomy is to look how the planet looks like in these different phases. When you talk about the magma stage, if you're familiar about the exoplanet population, you may have heard about 55 Cancri, which is a magma planet maintained in that state. There's a couple of planets that are quite hot, but not that hot, that would qualify very well in this stage, which is a partial melting stage. So we have a lot of planets here we can use as a reference to complete and study this. So this is becoming the interesting game, because you start teaming up with a scientist and try to assemble all the dots and making sure that together you build up a comprehensive view using what we know in great detail from Earth, what we know on Mars, and what we can get on the planet. What we can get on planet is something like that. There is pretty much predictions, this different stage. So if you have this preconception that a planet has a single atmosphere, in astronomy, we tend to see the universe as a static. We observe something and that's it. Well, when you deal with planets, they keep changing. Of course, we know the weather stuff and the season stuff, but I'm not even talking about that. I'm talking about the formal developments and the change into the atmosphere of a planet. So the atmosphere of a planet is dramatically changing in the course of its evolutions. And that is the expectation on Earth, according to the model that people have. Well, maybe we can test that, or partially, yeah. We can partially test that and combine all the data together to get something out of that. So this is exactly why I want to come in and here. So there is two words here, different, and there's two universes of people that are seeing things differently. You can look at this from the chemistry and biology, which is the top, and you see the evolution of Earth, the life on Earth and all the complexity of this. But you also see in this from an astronomy perspective. And what it would translate practically is in the diagram in the bottom. You would analyze the water, you would guess it never changed. You analyze the carbon dioxide, it changed dramatically. There is a rise of the oxygen, which is a dramatic moment, by the way, because at that time you end up in a kind of snowball because you stop the global warming and you end up with a very cold planet. And I think we survived this thanks for, I think, due to possibly the volcanic activity that, revived life. So at that point, you start to think about, you may have life, but maybe you can destroy it. So the fact you have life one day doesn't mean it keeps along and stay in the other day. So this is a combination how in astronomy we should see life. Not on the top, but the one in the bottom. And we should try to find out how it looks like, the story, how it looks like the story when you combine with the planet. So it's a very, very complicated problem because it's a complex problem. When you have to have a lot of dots, you have a very incomplete picture. But because of the fantastic tools we have right now, I think we can make progress. There is one thing missing. We don't know how to work together. And it's quite fascinating. As soon as you ask a biologist and a chemist and a scientist to give a talk to astrophysicists, how far they just misunderstand each other. Even the terminology is different. And try to fix that. We are trying to now challenge this. And we have tackled that very seriously and say, no, we're not facing a problem of discipline. We're facing a problem of structure of the whole academics words in the way the interdisciplinary challenges are difficult to get organized. Every kind of system is within silos, the way you do the fundings and everything. So we try to help that we've managed to set up centers and center of development, one in Cambridge, that's called the Labour Home Center. So if you want to have a detail of that, we made the official announcement this week. It's for 10 years, it's fully funded for 10 years right now. There will be a couple of initiatives, opportunities, postdocs, and please check the Twitter, check the accounts. And if you're interested into this topic, this is one way to do that. And if you want to know more, there's an ongoing activity in ETH Zurich these days. This will be announced during a symposium. I would invite you to attend if you're interested by the topic, which is a Lattice symposium, and I've been told there's still some slots free. And then we will expand on that on the 2nd of September, explain what's going to happen. Similar initiative exists in other places. There is one in Harvard, there's one in Chicago. Right now, there is a kind of a momentum into this. People are trying to use the resources and interests of these different disciplines to make them together. So that's the plan. I think we have a fun time. And as an astrophysicist, we have a big game to play here and to play together. And eventually, we'll find out something. Thank you.
Thank you very much. Thank you very much. So I like this session. Everybody's on time. We have time for questions. Please raise hands, wave hands. Come on, don't be shy. He's just a Nobel Prize winner.
Yep, somebody in the back.
Your eyesight is better than mine.
Yeah, well, have good glasses.
Hello, my name is Veselina Kalinova from Max Planck in Germany. So thank you very much for the exciting results and amazing review. I would like to ask, which are the constant conditions that we need to have, maybe except water, to have conditions for life?
You mean you're asking how do you get water on the planet?
No. Which are the other constant conditions that we must have to have life?
Well, I don't know. And there is two words that I'm battling right now, and I have not used it, if you pay attention. One of them is habitable zone. I think it means nothing, because essentially habitable zone is a reaction of the planet according to a specific assumption of the atmosphere, and you bring hydrogen, you change completely the habitable zone. So this is something we should stop using. And the other one is biomarker. I think, frankly, I have no idea what is a biomarker. I'm very interested if somebody can build up a global model of a planet, including the possibility of life having affected the planet. But I think this is really a complex problem. You need at the same time the planet marker, the mineral marker, and to really understand the biomarker. So I think the expectation that there is a magic, molecules that you could pick up and claim there is life, to my idea is wrong. I think it's wrong. It certainly can be used as a probabilistic argument, and we may end up having a lot of probabilistic discussions, saying there's a likelihood of this or that, and we compare all the planets look like that. Let me give you an example. Let's imagine we observe 10 planets like the Earth. And what we realize, they all look like Venus. A lot of CO2, very easy to find CO2. So that may be the first discoveries that we're going to get. What do you think about that? It's quite interesting, I think, already. So I think this is what we should be doing. We should just kill the preconceptions. We should stop talking about habitable zone. We should stop talking about biomarkers. We should just explore and assume the life is connected to the planet. And we're still far to understand all of this. But there is so much we can retrieve from the planet atmosphere. We should just go for it. Like getting this 5,000 planet, we keep detecting all of them. And I think if you look around the 500 nearby planet, essentially, very few we know anything about the planet system. There's a lot of transiting planets, but for 100 planets, there is only one transiting. So you're missing, it's the most inefficient technique you can think about it, but it's glad it works because we're doing a lot of great science with that. So I think we should really take the time to settle and to look at this and to team up with the people that know much better when you deal with life and try to refrain ourselves from abrupt and short statements and stop using this kind of terminology that means essentially nothing, I think.
Okay, thank you. There's the gentleman.
Many thanks for your exciting talk. And I have a couple of questions. One very small. There was, in your diagram about the planets, there was one planet with the size of the Earth and the mass of Saturn. What the hell is that? And another, what is your view about the idea of panspermia? What?
Okay, well, the first one is it's a good question, so I have no idea. I mean, according to my colleagues modeling this planet, they're very puzzled by that. And I could not reject the fact maybe there is wrong measurements here and something, but it could also be an extreme case of a specific planet with a lot of hydrogen. As soon as you have hydrogen in the planet, I mean, even if you have a rocky planet, you can expand the atmosphere dramatically. So the hydrogen make expansion of the atmosphere. So it could be a possibility. The panspermia, I know it's an old-fashioned idea. I kind of understand the idea that you may have some molecule moving around in the solar system because we do see, I mean, rocks moving around, and you can imagine some kind of complex entity moving with the rocks. I'm not too much shocked. And that will be a challenge if you find life similar on Mars. Would you conclude that Mars was the cradle of life and went to Earth after? So this is, but there's still another problem when you talk to my colleagues biologists about that. You know, life, it's not just something that comes like a magic. It's something that is a result of an optimization. So life has to dominate. They have to take control of the chemistry of the planet to develop. Otherwise, chemistry will go. Remember, chemistry always go. They never stop. So if you imagine something which is a complex chemistry falling on the planet which is not optimized, what is the chance of this to be just diluted? And that's it. So I'm not a great fan of that for that very simple reason. But again, it's by talking with chemists. But I cannot reject the idea that there certainly will be molecules falling on planets and even complex molecules in some case, because it is clearly the case. Yes.
Thank you. And yeah, I saw, and this is going to be the last question, because otherwise I'll be dead.
I don't want you to be there.
I'll be brief, promise. Thank you, Didier, for a really nice talk. My name is Bibiana Prinot. I'm a PhD student in Lund. So I was joining the Exoplanet sessions the past 2 days, and yesterday evening we had a panel with a really big question on finding Earth 2.0.
Yeah.
So I'm really wondering, what is your take on how are we going to do that? How are we going to find Earth 2.0? Yeah, when are we going to find it? Who is going to find it?
Okay, I don't really like the concept of Earth 2.0. I think this is a bit too simplistic. I think there will be a gradual improvements into detecting planets that are into the rocky, regime with longer period. The problem right now that we have is certainly the transit is kind of stuck on the short periods, and I think we should stop hoping too much with the transit for anything which will be longer than 60 days. So the only technique I know it works, which is the radial velocity, while it has not demonstrated, we have seen just before this fantastic result of Proxima. I think this technique is working. We just need to use enough telescope time to make it work, which is the challenge actually here. So I'm betting right now on what has demonstrated efficiency to explore the nearby stars and to look for planets that would be in a kind of Earth regime, but in a longer period. And that would be my bet, practically. Later, we have to face the reality that the atmosphere of the Earth, I think the bioatmosphere is 10 kilometers, the Earth is 6,000 kilometers, so there is really no hope at all that you find anything through by transit. And people hoping for TRAPPIST, for detecting life into a TRAPPIST system, I think they should give up. But I really hope that there is at least atmosphere, and very thick atmosphere. And I really hope that TRAPPIST is different with a lack of 300 kilometers atmosphere, because that one would be detected. And that would be amazing already to do that. But as soon as you get down, you will have to go for direct imaging. And there is no way out. But we have great equipment that is coming. ELT is coming, and the next generation of space telescope is coming. I think we are moving the right way.
Okay. Thank you. Thank you very much again. So our next talk is going to be by Zita Martins, and she's going to talk about recent achievements in the exploration of the solar system. I'm not going to read all of it. You're going to talk about it.
I'm going to talk. Thank you so much for the introduction. Thank you so much to everybody. So I'm going to talk about the recent achievements in the exploration of the solar system, but focusing mainly on prebiotic chemistry, habitability, and biosignatures. So it follows really well on the previous talk. And I'm sure we're going, after my talk, going to continue with the sort of discussion we were having right now. So first things first, we've seen this slide throughout the week that shows all the explorers in our solar system, not outside, but in the solar system throughout the years. And obviously there's been a mirage of information from Bepi Colombo on Mercury, Venus Express on Venus, and then with all the polemics about phosphine, obviously there was also new interest on Venus and whether there was the possibility of life existing there, which I don't believe personally, but that's open to discussion, obviously. And so ESA has in development the Envision mission with launch in 2031. In terms of the moon, there's been throughout the history lots of missions to the moon. Mars has been a focus on great interest, not only on astrobiology and origin of life, but other space missions. And in particular, obviously, we got lots of information from Mars Express and ExoMars from the TGO. There's been lots of debate, especially on Mars, in relation to CH4, so methane. Apparently, Mars Express detected a spike on detecting methane, and then the TGO said, well, honestly, we're not seeing constantly this, and even if it exists, it's most likely not a sign of life, but instead it might be a geological process. So the discussion is still ongoing. And obviously this is open of interest because CH4 may be an indication of formation and presence of microorganisms such as methanogenics. Obviously we'd love to have the ExoMars rover. It's been out of the ExoMars rover. It's been delayed, as we know, the launch of the ExoMars rover. Not showing up. Okay, back, of the ExoMars rover. Because of the war, it's been delayed, so we're all keeping our fingers crossed and see when we're going to have the rover landing on Mars. Focusing on here, obviously, there are a few future space missions that we are particularly interested. Comet Interceptor is going to visit, for the first time ever, a comet that has never entered the inner part of our solar system. So obviously, we're going to get lots of information on the prebiotic chemistry and actually trying to understand what happens in comets and whether they contributed somehow to the chemical feedstock of molecules to the primitive Earth. But that the launch is only in 2029, piggybacking the under mission aerial space mission that we heard about today. Obviously here we're also going to see JUICE and some other missions. But as I said, my focus on my talk is not about this general overview, but actually about prebiotic chemistry and how do we jump from there to having habitability and who knows, maybe origin of life. So in order to have prebiotic chemistry and to have organic molecules that were delivered to the early Earth and that may have contributed to the origin of life in our planet, there are different ways to have that and to study that above all. We either have samples from asteroids in our hands that land in our planet, so-called meteorites. And so we in the lab try to study which organic molecules are present in meteorites and try to see whether those organic molecules were important for the origin of life. I'm not going to talk now about that. I have an invited talk afterwards from 6 o'clock on, 6:10, on organic compounds in primitive carbonaceous meteorites. So feel free to show up. It's in session S9F. So I'm going to talk about lots of the organic molecules, amino acids, nucleobases, polyols. All those have been detected in primitive carbonaceous chondrites, and they have been brought to the Earth. But above all, I'm here to talk about space missions to actually know better our prebiotic chemistry in the solar system. So obviously, if we don't have access to meteorites, we should plan space missions to asteroids, which in some cases are the parent body of those exact meteorites. So here we're seeing an image of the Ryugu asteroid. This was taken by the Abusa 2 mission a few years ago. we know that this mission collected samples. The samples were brought to the Earth and then analyzed in different labs. Actually, 4.4 grams of the C-type near-Earth asteroid Ryugu were analyzed. There are 6 international initial analysis teams. I'm part of one of the team. I'm part of the insoluble organic matter. Right now, we are, as we speak, submitting articles, reviewing articles. So not much I can tell you officially. I'm sure the PIs of the mission later on in a few months will be able to tell you more. But for sure, there's been some preliminary analysis and published results. We can see, for example, the work of Queloz and colleagues from this year. They analyzed the Ryugu samples using the micro-omega hyperspectral microscope. And what they've seen is that they actually detected organic molecules. They have detected a strong feature at 2.7 micrometers, which indicates O-rich content, and also a feature at 3.4 micrometers, which indicates the presence of organics. And so this is at least a preliminary indication that there is chemistry in there, there are organic molecules in Ryugu, and more to expect, we'll see. There's also an invited talk by Rosario Baroneto and co-workers. They're part of the mineralogy and petrology stone team from the Abusa 2 team. So he's going to present his talk on S9F, so feel free to go and check some of the exciting results. So I want to show you also another image of another asteroid. This time, this is an asteroid, Bennu, and this was taken by NASA OSIRIS-REx mission. Again, the samples were already collected. It's on the way back to Earth, which, finger crossed, everything goes okay, and it will deliver samples back to the Earth next year. Preliminary results from the team from NASA have shown that, again, organics and carbonates are present in this asteroid. So why 2 different asteroids, and in fact, why are the teams in contact and collaborating? So you have 2 very primitive asteroids, carbon-rich asteroids, and we want to start building this puzzle of which organic molecules were present on the primitive solar system that may have been brought to the Earth and may have contributed to the origin of life on Earth. And so by studying meteorites, by studying different asteroids, we're starting to build this information. Obviously, this is not life. We're still far away when we study prebiotic chemistry, really, really far away. But the question is put, okay, if life originated here on Earth, why not in other places of our solar system? So there are different questions we need to put. First of all, when we plan a mission, a life detection mission, to any place in our solar system, what should we look for? And the answer is the basic unit of life. The cell is the basic unit of life. Obviously, when you plan a space mission, and if you check the list of instruments that are in a life detection space mission, you're not going to see an instrument there exactly looking for cells. What you're going to see is equipment that is going to look for the building blocks of those cells, the chemistry behind it. So we're going to look for certain amino acids, certain molecules that make up the cell. So that's trying to answer question number 1. Question number 2 is, where should we search? And so I placed here on the right-hand side this diagram on the question of habitability. And I completely agree with Didier when he said he doesn't agree with this notion of habitability zone. I placed this here just also to say I don't agree with it. Because if you look to our star, and you see here the Earth, the habitable zone would only include the Earth and a little bit of Mars. It would leave out other places in our solar system. I mean, in the future, and I'm going to talk a little bit more about that, we're planning, the space agencies, the international space agencies, are planning missions to the icy moons of Jupiter and Saturn. So if this was correct, then why spend time and money going to those locations, okay? And so following a little bit the discussion we're having previously, at least in our solar system, when we're planning a mission, it's not exactly a life detection mission. We had that in the 70s with the Viking mission. Right now, it's more about habitability. So having a location in our solar system that has the right conditions for life to start. It doesn't mean that that place has life. It only means that it has the right conditions. And the right conditions are liquid water. It's not just water. We can have water in the ice form. That's not what we want. We want water in the liquid form. We need minerals and nutrients, and we need a source of energy. And that source of energy doesn't have to be the sun. Again, let's look for the icy moons of Jupiter and Saturn. We're not considering in that case that the source of energy is the sun. There are other sources of energy, including geochemistry sources of energy. So carrying on with this, I'm going to just discuss very briefly locations in our solar system where we're looking for those conditions of habitability where life may have started. And so icy moons of Jupiter, obviously, including Europa. We know this image very well. We've seen it from the Galileo mission. And this data from the Galileo mission has been revisited a couple of years ago, where actually scientists have shown that there were geysers coming out from Europa. And so a geyser is an indication of the presence of liquid water on the subsurface of this moon. And so this is a reinforcement that this is a good location to go and search, at least for habitability, on this location. Other locations obviously include some of the icy moons of Saturn, including Titan and Enceladus, and as we'll see later on, there are a few space missions planned there. So also again, we've seen this, this image of Enceladus by the Cassini mission. We've seen obviously that the surface is an icy surface, but it's not very smooth. It's all full of cracks. And again, this is an indication that something is forcing the ice to break. And this is an indirect evidence that maybe there is a solvent below that is forcing the ice to break. So we have this other image, also seen as from the Cassini mission. And the Cassini mission actually on Enceladus has detected geysers, has analyzed the geysers, even though the main focus of Cassini was not actually to analyze the geysers of Enceladus, but he did. And among other things, he found very simple organic molecules, including methane encaged and surrounded by water. Methane, as I mentioned today, may have two main sources. It could be from a geological process when you have a rock called olivine reacting with water to give methane. So from the astrobiology point of view, this is not very exciting. This may exist, may be a process, but this is not very exciting from that point of view. But we can also have microorganisms, methanogenic microorganisms swimming in that subsurface ocean that may release methane from time to time. And then on the geysers, we're seeing that. So future space missions don't have to directly go to this subsurface ocean to actually know their composition. So the plumes are a really good way to try to detect if there is something, if there is life, or at least if there are the conditions necessary to life to develop. Based on that, obviously, as we all know, space missions take decades, years and years and years to plan. And in the meantime, we need to find alternative ways to help prepare those space missions. So there are different ways. Obviously, when we do space research, we can be in this very first square. We can either go to the International Space Station, or we can have space missions to the actual locations we want to study, either Mars or the icy moons of Jupiter and Saturn. But alternatively, there are other ways that we can work here on the Earth and help prepare those space missions. So we can actually have and go to planetary field analog sites that mimic one or two or three conditions from those locations we're trying to study. I'm going to speak a little bit more about that, just to mention also that there is a third way. The third way is space simulations, either here on the Earth with big chambers that mimic the conditions of those planets or moons we want to study, or alternatively, we want to use suborbital missions that for a very short period of time mimic the conditions, for example, of microgravity. But let me go into the planetary field analogs. Planetary field analogs, depending on which planet or moon we want to mimic, are spread out throughout our Earth. So here I'm showing you 37 analog sites. So number one here, it mimics some of the conditions of Venus. Numbers 2 to 21 are analog sites for Mars. Numbers 22 to 32 are analogs for Europa and Enceladus. And number 33 to 35 are analog sites for Titan. So scientists, especially working in the field of microbiology, biology, geology, etc., do field work, go to those locations, collect samples, and analyze them in different ways to try to understand what's going on with those conditions and if we can get any conclusions based on that. Okay, so I'm going to show you some of the analysis my team did. We went to the Arctic. We did field work in the Arctic region, a place called Kujura Peak, and we did that for a very particular reason. Obviously, the Arctic is very similar to Europa and Enceladus because it's an icy location, especially in the winter, obviously. But in addition to that, if you compare different locations where we collected samples from a river, bay site, an ocean site. And on the ocean site, the salinity is very close to 1%. And this for us was very interesting because according to the Cosmic Dust Analyzer on board the Cassini spacecraft, the salinity of Enceladus is also roughly 1%. So we thought, okay, this is a good analog. Let's use this to try to understand what happens on Enceladus and try to see if we can get any conclusions from here. So my PhD student, Queloz, she's about to defend her PhD. She went to the Arctic with a big team of colleagues, also from Portugal, from Canada, and samples were collected. And then what we did was to study the reflection of 80 different microorganisms. So we had samples from ice, samples from water, as I mentioned before, that were collected in Kujura Peak in the Canadian subarctic. We isolated those different 80 microorganisms, and then we tried to see if the different pigments that exist on different microorganisms may have different reflection spectrum or not, and whether that informed us. And so what we could do, we classed that on different boxes, let's put it like this. We had pink pigments, white, clear ones. So we did here on dot, 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 on blue, we had just the medium where the microorganisms were suspended as a control. And we put all the samples on filters. We measured the spectrum, which is called fresh samples. And you can see here the reflectance spectrum. You can see two very distinct peaks here, one here and one here, roughly at 1.5 and one very close to 2. This is due to the water present that decreases the reflectance, and this is just to zoom from this area. And then we let the samples dry in a filter, and I explain why we did that in a minute. And as you can see, the reflection immediately increases. So for dry samples, we have drier, and so the reflectance increase. We did this also for yellow pigments, orange and green. And in every case, the dry samples have more reflectance than the fresh one. So to summarize, we have fresh samples that have a weaker reflection than dry samples. This is due to the presence of water, and in particular at 1.5 and 2 micrometers. And why is this important in the big picture of trying to detect life in our solar system? Well, fresh samples are the equivalent of a planet like the Earth that contains water. On the other hand, if we have a dry sample, this is the equivalent of having a sample on a dry planet, such as Mars, and in particular, cold moons, such as Titan, Enceladus, and Europa, that on the surface, they don't have liquid water. So obviously you may be thinking, okay, when thinking about Europa as an icy moon, but that place has a very, very strong radiation environment. We're not expecting to find pigments, even if life exists on Europa, on the surface. But this may be important, this sort of study, because we may find traces of biological pigments on the near subsurface, not exactly on the surface. And this will be important for future space missions, including high-resolution image spectrometers present, for example, on the NASA Europa Clipper in late 2024, and also in some mission concepts like Europa Lander stereospectral imaging experiments. So all this type of study informs future space missions. So this is just to show that we were a cover of the Astrobiology journal last March. And so I would like just to give you a very brief and quick summary. So this summarizes present approved and concepts to locations, in particular moons of Jupiter and Saturn. We've learned a great deal throughout the years from Voyager and Galileo and Juno and Cassini, Huygens, obviously, but we need to look to the future. And the future is obviously what it's here in orange. JUICE is approved, Europa Clipper is also approved, and obviously Titan with the dragonfly going to Titan. That will tell us a lot about prebiotic chemistry and the potential of those locations having at least the habitable conditions. Obviously, there are lots and lots of concepts going around. None of this in blue here, blue-greenish, are approved. They're just concepts, but it's important to see that the community is thinking outside of the box and going into different locations. Just to tell you that in terms of Europe and ESA is already looking towards the future. And in particular, there is Voyager 2050 that has lots of plan into the future. And ESA decided to look into the topic of moons of the giant planets and planning what to do in 2050. So they have an expert team. We've met during this year. I'm chairing that expert committee. We're supposed to write a report until end of next year, where we will indicate and help ESA try to decide where to go in terms of the moons of the giant planets, whether to go to just one moon or 2 moons of Jupiter, of Saturn. So we'll see. Hopefully we'll be able to publicly tell you very soon what are our suggestions to ESA. So trying to conclude, we know that space missions to very primitive celestial bodies, such as an asteroids, they are fundamental to try to understand what is the prebiotic chemistry that happened on the beginning of our solar system. That obviously won't tell us about origin of life, but it will tell us about which organic molecules were present in the beginning and that were at least brought to the early Earth. That, together with other space missions, will inform us about the potential of life existing in other places of our solar system. And in addition to that, it is important to mention that when we plan space mission, we can't just wait 5 years, 10 years, 15 years for that space mission to happen. We also need to do work here on the Earth. And that's when planetary analogs are crucial, and they help space missions a lot in the validation of methods of detection, for biosignatures, trying to test instrumentation, and also trying to say yes or no for the payload of future space missions. So thank you very much for your time, and hopefully we have some time for questions. No.
Yeah, this
But I'm gonna
session
be
is
around.
great.
I'm around.
You have a stand as well, like
No,
Lisa?
no.
Yes, we do have time for questions. Thank you very much. That was really great. Oh, yeah, I see the first hand here. Can you please introduce yourself when you ask a question?
Hi, I'm Fabrice Motès from Paris Observatory. Maybe it's too speculative, I don't know, but do you think that the color of microorganisms in dry samples could have an influence of the color of the ground near the geysers of Enceladus?
That's one of the things we're wondering. What we've seen, obviously, the biopigments we have, the color was not changed, but the spectral signature was changed. We're wondering about that, if it makes a difference or not. I mean, obviously, we can't just look to a planet or a moon, in this case, icy moon, and say, okay, look, it's brown, therefore there is something there. Obviously, that's speculative, that's not science. So we really need to measure the reflectance spectrum in this case and say, what's the signature? Does he agree with our database? And that's why we were building, and we are building this database together with colleagues from Cornell. They have this beautiful database. So if you go to the article, you'll see that the database that colleagues from Cornell have on this. Thank you.
Thank you. Other questions? Over there at the back, yeah.
Hello, Maciej Bilicki. So regarding collecting samples from outside of the Earth and looking for life, we know that there are some organisms on Earth that can survive very harsh conditions, and in space in particular. Yep. So what are the measures taken to make sure that we don't contaminate these external samples with actual Earth organisms?
Okay, thank you for your question. So obviously space agencies, they have planetary protection officers. They're the best people to talk about that. So ESA has planetary officers, NASA, JAXA, etc. So there's been international discussion exactly on that. On forward contamination, meaning we don't take samples from we don't take contamination from here to there, and there is already in place. So there is a minimum amount that rovers, for example, have to obey. It has to be below that threshold. Obviously, we can't be sure that 100% of microorganisms and molecules are dead and disappear, but studies that are performed, they want to see that with that percentage that the agencies say, if it crashes on a planet, it doesn't multiply and doesn't significantly contaminate. Also, something else is whenever we have sample return missions, how do you curate those samples, making sure that those samples, if there are specific organic molecules or even forms of life, that they are contained when they arrive here on the Earth. So planetary officers from the different space agencies, they obviously discuss that, and there is also organizations such as COSPAR that have that discussion worldwide and make sure that the curation measurements are in place.
Thanks a lot. There's one more question, last one.
Thank you. I'm Lero Todilio, University of Western Cape, South Africa. So there's been talk of life connecting it to water, but that's essentially just water-based life, right? Life could come from completely different chemistry, and similarly, I guess there's talk of Earth as an analog of life, but Earth is also just a good starting point. You know, it could be a completely different planet with life. So I guess I'm just, I hope we are not, I guess, ego-centric as Earthlings and using and going that way.
Okay, thank you. Obviously, you need to start somewhere. So as you mentioned rightly, the Earth is the only data point we know for now that has life. And so everything, most space missions that I've showed today and that exist are searching for carbon-based molecules and forms of life, because that's the data we know. That's the first step. In the future, obviously, you can look for something else, but at least for now, it's all carbon-based and also based on locations that have water. An exception is the fact that we're going to have, or NASA is going to have, a mission called Dragonfly that is going to Titan. And Titan has an hydrocarbon cycle. So it's not a water cycle like we have here on the Earth. It's an hydrocarbon cycle. And obviously, we don't know what to expect. We don't have enough data on Titan on that. But it will be interesting to study at least the prebiotic chemistry and whether any forms of life may have developed there that are not water-based. So we have to wait for a dragonfly. I'm particularly excited to see the results of that mission and wish good luck to the colleagues, because I think that's a wonderful mission, a little bit outside of the water-based thing that we've been looking until now.
Okay, thank you.
Thank you.
We need to move forward, but yeah, please find Zita. I think I will, because there were plenty of interesting things. Now there is that, yeah. The next part is we need to present, well, it's my honor and pleasure to present the EAS Tycho Brahe Medal to Jean-Luc Starck. So I need to take it, and then we can take a picture. Sorry. Where do you want us to stand? So this is the diploma. And this is the medal. So congratulations. I'll take those for you for now. I'll give them back, I promise. And Jean-Luc is going to talk to us about astrophysics from wavelets to deep learning.
Okay, thank you. First, I would like to say that I'm very honored for having this prize. And I would like to thank the EAS and the EAS Prize Committee. But also, I would like to thank all students, postdocs, collaborators, colleagues that I had for all my career. I think that all the work that I could have done during this time is thanks to them. And also the pleasure I had in my work is also thanks to them. Human interaction, I think, is very important in our field, and it's also what makes our job so nice. So this is also a recognition of the astrostatistics field, which has emerged in the last 30 years, and also about wavelets and sparsity. So I wanted to, in these talks, to make more like to show you the evolution of the idea in this field rather than presenting the last recent work. So this is the idea to present about wavelets, sparsity, and some kind of results. So astrostatistics, I think we can clearly say that as almost everything, it started with the ancient Greeks. And Tycho Brahe, from what I read, can be considered as the inventor of both database and data. So that's somewhere, it's also recognition with the Tycho Brahe Prize for astrostatistics. So for 3 centuries, astrophysicists and statisticians, I would say, it was the same people. In the 20th century, there was clearly a divergence between statistics and astrophysics, and not too many connections, and astrophysicists or physicists were even quite skeptical about statistics. For Rutherford, if an experiment needs statistics, we should have a better experiment. So that was the kind of spirit that people had a few years ago. In the late 20th century, situation changed because also there was much more data, surveys coming on, and we needed new techniques to extract scientific information from the data. So at the beginning, it was very similar to what we heard with Didier in the previous talk about the difficulty of communication between scientists from different fields. And I will remember the first conference where statisticians were presenting theorem to astrophysicists who didn't understand anything what they were presenting. And with a huge amount of effort, we could end up with a better interactions with the International Astrostatistics Association. And in EAU, there is also a Commission B3 now. There are some John Lab, Astrostatistics Lab, as a Cosmosat Lab at Saclay. So there is a lot of effort that have been done. And I think now we have developed really young people who are really at the interface between the two fields and can provide very nice results in astrophysics using very advanced statistical tools. So when I started to work doing my PhD, it was a fantastic time, exactly as now, because now we have the James Webb telescope which has just been sent. At that time, it was a Hubble Space Telescope. And for the youngest people here, they don't know that the Hubble Space Telescope had a huge problem. And on the left, you can see the image of a star. And you could see that the optic was very bad. And 3 years later, a shuttle has been sent to space to fix the problem, and the same object is observed after fixing the optics, and you see that it's much better. So for 3 years, the data was awful, and they had all to be deconvolved. And here is an example of an image before deconvolution and after the deconvolution. And this work has been done by Rick White at the Space Telescope Institute. And what is interesting is after 3 years, when it has been fixed, we had beautiful images. So you see the image before and after correction of the optic. But then it was interesting to see how the deconvolution was working. And here is now top the bad image before the optic has been fixed, and the deconvolved one at the bottom, then the new one after correction. And what you could see first is that the deconvolution was working very well. And finally, fixing the optics didn't bring too much resolution at the end. The deconvolved image before repairing the telescope brings the same resolution as the fixed image. What we had after fixing the optics is a much better sensitivity. But in terms of resolution, the deconvolution was already able to recover what was lost with the optics. So the next point was that we could even push forward the resolution and deconvolve the new image, and that's what we have on the right. So all these results were obtained using a new mathematical tool called Wavelets. And Wavelets were coming from French mathematicians, first Jean Morlet, and also Stéphane Malin and Yves Meyer later, where the idea was to replace the Fourier basis, which is stationary, by something which is more localized. And the idea was to decompose a signal or an image on a set of basis functions which was completely localized, and then you can dilate or contract this function. And then you get a new way to represent the data, where you can go from a signal to the coefficient, exactly as you are doing with the Fourier transform. You go from x to alpha, and then you can work on alpha and go back to x using the inverse wavelet transform. Or you can write it in a matricial form. Everything is linear here. So that was the way that you can represent differently data. And what it changed is also the way we model the data. So here you have an image of Saturn. And if you look here, the histogram of Saturn, you have this kind of plot here. But if you take the wavelet transform and you make the histogram of the wavelet coefficients, this is, this is what you get. So most of the coefficients are close to 0, and few wavelet coefficients are in the tail of the distribution. So this is completely a non-Gaussian distribution. It's a Laplacian distribution, where most of the information is in the few coefficients which are in the tail. So if you sort the coefficient from the largest to the smallest one, there are few large coefficients which contain most of the energy of the image and many small coefficients. To better understand this, imagine we take this image and we keep only 1% of the pixel with the highest value. This is what you have on the right. Now we do the same after taking the wavelet transform. We take the image, we take the wavelet transform, we keep 1%, and we put all the other coefficients to 0, and then we go back to the image, and this is what we get. So with 1% of the coefficient, we could keep 99% of the energy of the image. So this is the kind of thing you can do with the new modeling of the image. So how to use this modeling for recovering for deconvolution, for instance? You have a deconvolution problem where you have y, which y are the data, equal hx. H is your operator, your beam of your instrument, your point spread function. And now you say that your X can be modeled in the wavelet space. So you say that X equals phi alpha. And then you plug this into the equation. And then you introduce a new term here, which is the L1 norm, the absolute value of all the coefficients. And this norm is well known to reinforce the Laplacian behavior of the signal. So just doing this, we were able to get this deconvolved image and to remove the noise in the deconvolution process. So this is what we were able to do in the years 1990. And at the end of the years 1990, there was ideas of, can we do better than the wavelet transform? To replace the phi, which is here, by another basis, which would be even better than wavelets. And then the whole, I would say, signal processing and statistical community was working on different kind of what you could call X-led transform, where you decompose your image. And the whole idea also was to try to better represent edges, filaments in data, because wavelets are good for isotropic features. And for instance, the curvature transform allows you to decompose an image on basis functions which have this shape. So there are different directions and different size. And you have exactly the same as with wavelets. You have coefficients using the fast transform and a reconstruction associated to the transform. So you can play the same way with filaments. Or for instance, if you have this image, you take the curvature transform and you artificially enhance some coefficient, and you can now much better see all the elongated features in Saturn. So that's the kind of thing we were able to do. And we could try to use both wavelets and curvelets, and the idea was to separate the features depending on the morphology. And this is a hair shell image which contains filaments and forming stars. And just using both curvelets and wavelets, you could separate the stars from the filaments. And my colleague, Philippe André, could investigate how stars are forming along filaments. That's that kind of thing that could be done completely blindly using these new techniques. You can do this also in a multi-channel framework. So where here, the goal was to make strong lensing study, and we could separate the gravitational lens galaxies from the foreground using a multi-channel techniques based on the same kind of idea. So these kind of techniques were working quite well. At that point, they were lacking some kind of theory. And this came in 2006, which is called the compressed sensing theory. And this is due to colleagues in Stanford, Emmanuel Candes and David Donoho, independently. And what they have shown is, what they have proved is a theorem which says that we can recover a signal X, or alpha here, which is k-sparse, which means that there is only k coefficients different from 0, but only with k log n, where n is the number of pixels, measurement. So we can have much less measurement than you have pixels in the signal, and we can still recover exactly the signal. So this is very strange if you have learned that we need as much equation as we have unknown. But if these two principles are followed, that the signal is k-sparse, and we make what you call incoherent measurements, then we can recover exactly the signal, even if you have less data. So this theorem pushed a lot of people to use sparse recovery techniques to reconstruct the image. So one very nice example is radio interferometry. So radio interferometry, you observe, you have a subsample in the Fourier domain. So you can see that your acquisition matrix H is a Fourier transform plus subsampling, and then your signal can be sparse in the Wavelet domain. So the compressed sensing theory tells you that this is the kind of example where sparse recovery should be very efficient. Because anything which is quite compact in the direct space will be spread out in the Fourier domain. So this is kind of incoherent or quasi-incoherent measurement. So this is what we did a few years ago. We use compressed sensing for LOFAR data. And here, that's the Fourier coverage that we had. That's the inverse Fourier transform here on the data. Here is what was coming out from the pipeline, the LOFAR pipeline. And here is, on bottom right, here's what we get using sparsity. So what we can see is you have much more features in the recovered image compared to what was provided by the pipeline. So the question was, are these features right, or are they artifacts of the method? And here we got other data from VLA at a better resolution. And here we have the VLA image in contours, and the sparse recovery is color. And you can see that it's exactly the same features. So it was like a proof that it was working extremely well. Another clear and interesting application of these ideas is for when you are looking for harmonics in the Fourier space. So for instance, exoplanet detection or the kind of thing, we are always interested in finding harmonics. And generally what happens is you don't have information everywhere. So this is the kind of signal you can have, and because you have some missing data, so you can have a lot of artifacts which are the same location as the harmonics that you are looking for. So here, it's a kind of dual problem of the radio interferometry problem, and here you have harmonics, alpha, and you have the inverse Fourier transform and the subsampling, and then you have the measurement in direct space. And here, you can use the same kind of techniques, and this is the work that has been done by Rafael Garcia using the software we have developed in my group. And you have here in red the simulation, the real signal, and in black here, this is what you have because of the missing data. And here on the right is what you recover using sparse techniques. So we can really recover the signal of interest and the harmonics which were in the data. So these kind of techniques now are really in the pipeline of different projects, and they are really used massively for this kind of programs. What is also interesting is sometimes the instruments act as a compressed sensing measurement matrix. For instance, for gamma ray data, you cannot focalize the photons. So what you do is you put some coded mask on top of the telescope. And the effect of this coded mask is diffuse the photons. And here, for instance, the kind of data we have with the integral satellite, and this is the coded mask that was used with integral. So this is clearly a pure example of compressed sensing where you have a complete matrix which makes incoherent measurement. But here, because we are building the mask, we can try to go more in the direction of the theory, to make everything even more random. And this is exactly what my colleague Stefan Chan at CA is doing. And this is the mask that they are proposing, or even developing, because it's on the telescope now, that they are sending next year, the SWAM satellite. And you can see that the mask is highly random. And this exactly goes in the direction of the theory, which tells you that you should avoid regular pattern and diffuse at best if you can. So I would say that at some point we were very proud, right? You have a new modeling of the signal where we replace the standard band-limited Gaussian distribution using a sparse modeling. We had before the Shannon-Nyquist sampling theorem, which is replaced by the compressed sensing theorem. And to solve the inverse problem, we replace the standard T-square or L2 norm regularization by the nonlinear L0 or L1 regularization. So everything was beautiful setup, and we were ready to address the problem of the 21st century. But now what happened? Everything has to be done again, right? Because now we have deep learning coming up, and what you have is you have a much complex modeling, which is derived from the training data set. We don't have any theory anymore, and we have deep learning solution coming out of the neural networks. So we are we enter now in a new phase of astrostatistics where the learning has a very important place. So we have been investigating about these kind of things. So for inverse problem, one neural network has been quite famous. It has been proposed in 2015, and it's funny to see that the researcher who proposed this neural network is coming from the wavelet community. And you can see that here, there are some similarities with the wavelet decomposition, because you have the multiscale approach, where you have signal at different scales, and you have this residual connection, which can be seen as wavelet coefficients. So we have the filling, and there is also the ReLU, which is a kind of thresholding. So we have all the ingredients of sparsity are included in this kind of neural network. But there are also some big differences. There is a massive learning. So there are many filters which are learned, while with wavelets, we have only few filters per scale. There is a highly nonlinear processing. There is thresholding after each filter, which we don't have with wavelets. And there's another difference, is with wavelets, we have exact reconstruction that we don't have or generally we don't have with neural networks. And this also can have some impact in some application. So we have been working in my group as well on deep learning, and here is the first deep learning techniques applied on real data, on the DES data, and you can see here what DES was doing before, the kind of Wiener filtering, and on the right you have the deep learning techniques applied to weak lensing data. And what you can see is clearly we can have much better features at high resolution compared to what we were doing before. So that's a kind of nice result we can have using deep learning techniques. Deep learning is perfect. Clearly, some people believe that it's not. And there is some paper which show that we can have some very real effect. For instance, that's a paper where they tried to use deconvolution it was for MRI images. So they put the training data contains only ellipses. That was the training data. And then on the data, the simulated data, what the author did is they put, first a small picture and then some letters. It was a SIAM conference, so they put SIAM as a letter. And then here is what they got using deep learning. And here is what they got using sparsity. And you can clearly see here that sparsity could do much better than deep learning. And the reason why is because the training data that was used for training the neural network was not perfect. So there was something unexpected in the data, and the neural network was not able to recover it. While a kind of more traditional technique like sparsity was completely agnostic to this and could recover very easily the data. So I also did myself an experiment. I have a very machine learning student who believe only in units, and I asked him to train a neural network for me, and I gave him an astrophysical image, a simulated data, with noise, and he gave me the denoised image. And this is on the right what you have, while Wavelets was doing much, much, much better on this image. Okay, so again, the neural network was not trained for astrophysical images, and then it didn't provide any good results. So this was a kind of extreme case, but it just shows that you have to be quite careful. You cannot just trust exactly how it comes, and you have to take some consideration and to be cautious. So to conclude on my talk, I would say that astrostatistics is a well-established field now. I've been speaking about sparsity, compressed sensing, but there was many other things going on. People working on Bayesian techniques, for instance. Cosmology is fully based on Bayesian techniques, so there was a lot of development as well. Sparsity and compressed sensing have been very efficient for inverse problems. And also what I found very interesting with the compressed sensing theorem is also open the mind for designing instruments. If you cannot cover with CCD the whole space, or just because for physical reason we cannot focalize the photons, compressed sensing can help us to design new hardware. And that's what I think was very interesting, to have the joint hardware and software design. And obviously, every time you can have a good representation, it improves the results. This is also a kind of message of my talk. And deep learning also can help to have a better representation. If you have an idea of what you are looking for, we can really design a very complex modeling of the data that we were not able to do it before using, I don't know, wavelets or curvelets. So all these techniques clearly represent the future, deep learning techniques, but we need to be very cautious. That's another message, especially for inverse problem. There are some problem of hallucination, for instance, that exists. There's some problem of generalization. And sometimes there is a trade-off between performance and generalization. And you have to be aware that there is this trade-off to be done. And depending on the application, you have to choose exactly what is the appropriate tool to analyze the data. That's my last slide. What is the future? So as I mentioned, generalization problems, the lack of interpretability is clearly a challenge for the next decade. How well we can generalize the tools to unexpected data. For instance, imagine that the neural network is providing a kind of very different results. For instance, no agreement with general relativity. Do you trust the neural network or not? That's the kind of question you should consider. I saw in this conference many, I don't know, at least few talks trying to insert physics in the neural network, and clearly that could be a right way to do, to have something which is more driven by physics, and I think that's an important point. Another aspect of neural networks that you should be really careful is the concept of reproducible research. I think it's more and more important to have all our results reproducible. It means that everything should be on the web, the data we are using, the scripts, and the software that we are using to produce the results that are in the papers. This concept of reproducible research is even more challenging with machine learning. It's very hard to reproduce results because not only you need the neural network, but you need the parameters, you need the training data, the parameter for training the data and everything. And it's very rare that all the information is there just to reproduce the neural network. So that's clearly a challenge as well for the community. Another aspect is frugality. More and more we discuss about energy, you have to preserve the resources. So a few years ago, I was denoising my data with my simple computer in a few seconds. Now you need to burn GPU on a cluster of GPU to burn hours of computers. So you should also consider if sometimes the improvement worth the energy we spend. And the frugality is also something to put in the equation when we decide which tools we should use for analyzing the data. There is this sentence of Occam, which is very known by Bayesian, but here could be used in another way. Is when to do with more what we can do with fewer. So if we can do almost the same with less energy, less computer time, then maybe that could be a way to do. And I thank you for your attention. I was not expecting so many people for the last session. Thank you very much, and I will be happy to answer any question.
Thank you very much. That was a great talk. Questions? Do I see hands going once? Oh, come on. Yeah.
There is one there. There is one there.
Where? Stand up, please. Yeah. Okay. Yeah, we saw you. Thank you. Turn on your microphone.
Okay. I guess the question may be a bit naive, but I was just wondering, so what do you think about the potential of combining basically the scattering transform and the wavelet transform with the existing neural networks, i.e. feeding them in as additional layers for a unit or something like this?
Okay, so for people who don't know, the scattering transform has been a new transform which has been proposed by Stefan Mahler, the pioneer in the Wavelet domain. And the idea of the scattering transform was to capture correlation between scales. So he found a way to capture this correlation between scales, and it is based on wavelets. So somewhere the first layer of the scattering transform is a kind of wavelet decomposition. So it's a kind of extension on the wavelet transform. At this stage, I didn't see any results in cosmology where the scattering transform is better than other techniques. It's better than the power spectrum alone, but it's not clear if it's better than other techniques like peak counts and everything. So I'm somewhere, I would like to see first result before saying that we should go these directions. I saw a nice result with the scattering transform for simulation. Because they were able to capture correlation between scales, they were able to simulate data on, I think it was the magnetic field or the galaxy or something like that. It was about our own galaxies, turbulence, kind of thing. That they were not able to do. People also tried the scattering transform from classification, and also in classification, scattering transform was not state of the art. So I would say that scattering transform is interesting. Now the limits of the method are still to be defined. So for cosmology, I'm not so sure. We'll see.
Okay, thank you. Another question? Yeah.
So I really like this because I mean, especially for the application to the radio astronomy. So I hope I don't regret asking this because I'm really out of the field here. But when you're starting to show the examples of the sparse sampling, I was hoping a slide on CMB and how it will behave. Was that tried or?
Okay, so I've been working for years in CMB in Planck, and there was some people were quite conservative in the CMB community on sparsity. Even if you had very nice result for component separation, for instance. We have some papers, and we have also a CMB map available from the Cosmosat webpage, which is very, very clean. But yeah, it can be used for CMB. It can be used for in-painting, if you want to in-paint the missing part, the mask, or this kind of thing. It can be used for component separation. I know that people want to work on the kinetic Zelovich effect, have to have very clean CMB map, and they were using our map for this kind of application. So the answer is yes, it's useful also for CMB. Maybe now we could do better with deep learning. Some people are investigating deep learning for component separation, and I guess we will have very nice results in the future.
Okay, thank you very much. We need to move to the closing ceremony, so let's thank Jean-Luc again. And I'll give the floor to my colleague Agata, who's going to chair the closing ceremony. Thank you.
Okay. My name is Agata Rozanska. I'm from Warsaw, and I have this pleasure to make a closing ceremony. So good times and quickly. This probably exists in any language, and I don't have to explain everything, but well, we should start with poster winners first. Okay, so EAS each year sponsors the prize for the best poster. And also on this meeting, we had voting. You could vote for e-posters connected to each session. And the winners are ex aequo 2 people. The first person is Artemi Camps Farina from University of Madrid for the poster titled Variable Metallicity Yields in Stellar Population and Tracers of Inflows. If the person is present still, please come here or show up. And the second ex aequo winner is Sanya Khan from EPFL Switzerland for the investigating Gaia EDR3 parallax synthesis using astroseismology of cold giant stars observed by Kepler and TESS. Please, if Sanya is here, please come in. Congratulations, and you are getting your prize in the registration desk, okay? You can go there.
Thank you.
And until 7:30, you can go and pick up your prize. It will be the book. Okay, Sanya is not here, so we can move to the other awards. We had this application and gamification results. And so please, can we have a movie now? Because as you know, our meeting is partially hybrid, so the gamification results will be given by the movie. It's coming. We have 4 prizes. And the first prize, free registration for the next meeting in Krakow, goes to Mr. Sang-Sing Cheng, University of Bologna. Congratulations. The second prize, free gala dinner ticket for the next EAS meeting in Krakow, goes to Mr. Keegan Thompson Paraseni, Observatoire de Paris. Please give your email address. I mean, the voucher will be sent by emails to you. The third prize, EDP science books, go to Mr. Marcin Wrona, Astronomical Observatory, University of Warsaw. Congratulations. And the last prize, Springer books, go to Mrs. Fabiane Neil, Observatory of Amsterdam. Congratulations, and all you are asked kindly to go to the registration desk to pick up your awards. And now I would like to invite Roger Davies to summarize our wonderful meeting.
Thank you very much, Agata. I won't try and summarize, but I will make a few remarks. The first remark I want to make is just to thank everybody for their care with COVID. I'm looking out. Most of you, almost all of you, are wearing masks. It's not terribly comfortable. I did it all week. It protects us. I also want to thank you for your full adaptability of the organizers. Because of COVID, there have been various changes at the last minute that have had to take place. It's been pretty seamless, and so well done, everybody. It's been a terrific show all round. And it's a record-breaking show. We have 1,766 in-person participants at this meeting. That's way more than we have ever had. There are about 500 students here, and actually probably a similar number of early career researchers. I don't have the exact number, but it's probably more than half the people at the meeting are early career researchers or students. And one of the things I noticed when I looked through the statistics is that most of you are not members of the EAS. Now, if you're a PhD student, you can join as a junior member, and if you have a PhD, you can become a full member. And of course, it's free if you're a member of your affiliated society. So I kind of have a double message here. Please let us know why it is you haven't already joined, as it were. Send me an email or send Mark Odar an email and just explain why, if you would. But also, probably even easier, join your affiliated society and automatically become a member of the society, because then you can participate in all the things we do. Okay, with that plea, I'll move on. So there are two things that characterize this meeting which are quite different from most other meetings. The first one is, I've nearly already covered, which is this is a young meeting. There are an enormous number of young people at this meeting, and I can't tell you how gratifying that is from my end of the age spectrum. It's fantastic to see our subject attracting so many young people. The other aspect, which you do see elsewhere, but not in that many meetings, is the very broad agenda of this meeting. Not only, I mean, it covers a huge swathe of astronomy, one end to the other of the electromagnetic spectrum, from asteroids to cosmology. It's exceptional. And one of the things, I shall come to this in a moment, but you know, I'm very fortunate. I work in Oxford. My subject is galaxy evolution. I can go to endless numbers of galaxy evolution talks in Oxford. What I use these meetings for is to find out what's going on elsewhere. So I've been dipping in around and seeing what's happening. Before I move on to that, though, I should say that the plenary talks and the prize talks have been absolutely outstanding at this meeting. They're from the people at the top of the field, and I think we should give all of them a big hand. So this is the next little section of my remarks. Obviously, is going to be a personal view. I roamed around the various parallel sessions a little bit, sometimes randomly, sometimes just following my own sort of interest that I've had in the past and so on. So I had a bit of background. And I was really struck by both the scope and the grasp of what is being done in contemporary astrophysics in Europe. It's incredible. Michel Mayor explained to us how we could determine the orientation of the orbit of an exoplanet compared to the spin axis of its host star. Just think about that for a moment. That is a remarkable thing to be able to do. We can identify the stars that are in the streams going around our Milky Way that are the remnants of the satellites that have been destroyed by it. Quite astonishing. By the way, when I was in the tidal streams session, I have to say, I really admired your fortitude. It was very hot in there. Thanks to Gaia and the ground-based spectroscopic follow-up, we have an unparalleled view of a subject that, you know, was very present when I was a young scientist, but had certainly had a dip in between, the understanding of open clusters. Now, the precision of the measurements relevant for that subject that can be made is absolutely breathtaking. I have to say that there was also a very insightful comment by one of the people who gave a talk while I was there, which was that although the measurements that have been made were much more precise, 10 times more precise, than those that had been made before, because, of course, that's not the only thing you need to increase understanding, it turned out that the accuracy of the results was actually roughly the same. And so that's because the modeling didn't include all the effects that need to be included. And this is a wonderful example of how our subject moves forward in steps where observations make progress, theories have to catch up, and vice versa. The future of that field, and many other fields in galactic and extragalactic astronomy, looks very exciting. We have WEAVE coming along, Foremost, and MOONS will come into use in the next few years. We saw the remarkable results from the Event Horizon Telescope, and of course, we're all anticipating the results from James Webb, which are now only a few days away. So there's a common theme here. Advances in technology make opportunities for us to make advances in astrophysics. Our role, what do we do in this system? We provide the creativity. We are the people that can look at new ways of doing things and draw new astrophysical conclusions from new data that comes about from the application of new technology. Of course, there's a great deal of creativity that goes into the generation of that new technology as well, and we participate in that too. So look, I don't want to portray a picture of everything that went smoothly. I've already mentioned it got rather hot in one of the rooms, and I noticed that the machine learning room got very, very busy at some times. Not everything works perfectly. These are the challenges of success. We have a lot of people here, and it's very, very hard to predict in advance who should be in which group. Actually, these problems were solved remarkably quickly, and we'll continue to work on them for future meetings. So I should also say a few words about sustainability. We had a pretty robust discussion at the General Assembly about sustainability. The Council of the Society is certainly committed to offering an increased hybrid offer as we go from annual meeting to annual meeting. It's very difficult to predict when a fully hybrid meeting will be possible. That's an area that's advancing very quickly, but it's somewhat out of our control. We need to be in a big center like this to meet, and so we will continue to go as rapidly as is prudent. I want to make a few comments about Africa. We've had the third in our series of bi-yearly sessions on collaboration with Africa, and I want to sort of put a challenge out to you. So we have a couple of years now before the IAU General Assembly in Cape Town. And we have a number of programs underway to expand collaboration with the African Astronomical Society and with astronomy in Africa. Of course, the IAU in Cape Town will probably emphasize the astronomy of Southern Africa. Whereas, of course, here in Europe, we have a rather special opportunity because many of our scientific contacts are with North Africa for the obvious reason that it's just across the Mediterranean. So I'd like you to think of ways in which we can enhance what African astronomers can do and think about that so we can make a contribution in that way to the General Assembly of the IAU in 2024. Okay, so now I have a lot of people to thank, and principal amongst them are our local organizers. So Jose Carlos Guiardo, Francesca Figueras, and Emilia Ortiz Gil, please stand up and take a big round of applause. I want to thank our exhibitors and our supporters. They are loyal. They support us at every meeting. We really appreciate their support. It's great to see them again. We have not seen them for, well, it's 3 years now. So it's wonderful to have you here with us. I would also like to thank the people who work all year for this effort. That is the annual board. And the annual board is a combination of council members from the EAS and the local hosts. So please, the people who work on the annual board now are working on the next meeting, the meeting in Krakow. They work all year to make these meetings possible. Please will you stand up if you're on the annual board and take a round of applause. Of course, one of our supporters this year, of course, because we're here in Valencia, was the city of Valencia, and I certainly want to thank them for their contributions. Then I want to thank two people in different colored shirts, or two groups of people in different colored shirts. First of all, the volunteers in the orange t-shirts. You've run around all week to keep the meeting going. Please stand up and take a round of applause. And finally, the people in the black t-shirts over here are partners from Kuoni Tumler. They work also all year to make these meetings possible. They come to the site visits and so on. They arrange so much of the meeting. They do a terrific job for us, so please thank them. Okay, I do hope I haven't forgotten anyone. So I now just want to remind you that we're meeting in Krakow next summer, the 9th to the 14th of July. I just want to remind you about Krakow, right? So everybody knows that the most famous Polish astronomer is Copernicus, but perhaps you don't know that he went to university in Krakow. So he went to university. Actually, he was quite young when he went to university, about the same age young people go to university today. And if I understand it, it was the University of Krakow at the time, but I believe now it's the Jagiellonian University. Is that right? Yes, so that's why the Jagiellonian University is playing a key role in next year's meeting. So look, with that, I will thank you all very much for coming, and I hope very much to see you again in Krakow next year. Thank you.
Thank you, Roger, very much. And now the very short summary by Jose Carlos Gurida, a chief of all chiefs here in Valencia. Please.
Well, it's been an intense week, definitely. So as a host representative of the host committee, I would like you to go back to Monday afternoon. Those of you that were here, remember that we had those dancers and those acrobats, the musharanga that we have. They form human towers, whose importance is not measured in just the height of the tower, it's just a number, but in the plasticity and the quality of the execution. I would like to make a parallelism with this meeting. We had 1,800 participants, like Roder said. It's a record of participants, I know it's important. But it is more relevant than the quality of your participation. You can be wonderful participants, not only science-wise. All the events proposed in parallel by the host committee has been very well received, largely oversubscribed. We are delighted with this. As a host committee, we have tried to add a layer to cover this meeting with some of the Mediterranean culture, a culture of sound, tradition, science, remarkable architecture, and, well, a bit of fiesta. Our initiatives were addressed to share with you our way of living. We expect to have accomplished this. Well, it's time for acknowledgement. Well, I would like to, also we have to thank to our local institution, the City Hall, Valencia City Hall, the Valencian government, our host institution, the University of Valencia, with the Astronomical Observatory, the Astronomical Department, and the Institute of Particle Physics. They support us in this adventure. And finally, we would like to thank, although Roger already said to Quoni, the company organizing and helping us with this meeting. I would like to call to the stage to Laurie, if he's here, I think, and Amelia, could you come in also? With the Laurie is really the chair of the meeting. It has been a wonderful job for us. Thank you, Laurie. And there is also some little gifts for the rest of the team. There are some Spanish fun. I will tell you the instruction later.
Thank you, Jose Carlos. And now final remark about the future meeting, which will be in Krakow. And of course, I'm the first time attending meeting in person as the member of council. And I know we have to learn lessons for the future mission. And the one lesson we learned, we put our conference center closer to the city center. But this is the only maybe better location, but all other things in Valencia were wonderful, and I don't know if we are going to bet them. But there are two reasons to keep the next EAS meeting in Poland, because 100 years of the anniversary of Polish Astronomical Society and 550 years from the birth of Nicolaus Copernicus. And, okay. And beside of this, Krakow is really great town, so I hope you will have good time, good scientific communication, and good networking. And so the final thing we should do, it's to move EAS flag from Spain to Polish representatives of Polish Astronomical Society, Milena and Łukasz. Please. Milena Ratajczak and Łukasz Wyżykowski from Warsaw from Astronomical Observatory University of Warsaw. Please take a flag. They represent a flag. Take to Krakow and make next meeting possible. Thank you very much and see you next time.
Anytime you touch it, it will pop up. So this is
Imagine there's no heaven. It's easy if you try. No hell below us. Above us, only sky. Imagine all the people living for today. Imagine no more countries. It isn't hard to do. To kill or die for. No religions too. Imagine all the people living life in peace. You may say I'm a dreamer, but I'm not the only one. I hope someday you will join us, and the world will be as one. Imagine no possessions. I wonder if you care. No need for greed or hunger. A brotherhood of man.